Hi everyone, Dr. P here, and in this lecture video we're going to take a look at matter and its relationship with light. So now in the 19th century view, late 1800s, matter was made up of particles and was distinct from energy. So if we have matter on one hand and light or electromagnetic radiation on the other, matter is a particle and thus has mass, whereas light is a wave and is massless. And then matter also has an identifiable position, whereas light is delocalized. Now, there were some experiments that cast doubt on this model. And I'll just mention them here. I'll talk about them. I'm not going to write out the details, and you can read those details if you want to make some notes on them from the text. First, we had Planck and blackbody radiation. And so Planck was a scientist in the late 19th, early 20th century. And he was studying light emission from heated solid bodies. So he'd heat things up until they glowed and then examine the wavelengths, frequencies of light emitted. And the results were not explained by classical mechanics. That is, he was expecting continuous spectra, but instead did not see continuous spectra. Instead, there were distinct frequencies, wavelengths of light that were emitted. And so he postulated the quantization of energy. That is, energy in the form of light is gained or lost in this blackbody radiation experiment in whole number multiples of h nu. And h is Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. And if you're a physics major, you may be acquainted with that. So delta E, our change in energy, equals some integer times h nu. So n equals 1, 2, 3, etc. Now another experiment that cast doubt on this model with matter and light from the 19th century was the photoelectric effect. And it was Albert Einstein who explained the photoelectric effect. Now, in the classical or 19th century view, the energy of light is proportional to the amplitude of the wave, that is, how high the wave is, or how large the wave is. But the experimental result was that when you shine light on a metal strip to generate charge, that is, knock electrons off of the metal, only light above a certain wavelength, which depended on the metal, would light below a certain wavelength, above a certain frequency, would work. So light above a certain wavelength or below a certain frequency, lower in energy, wouldn't work. So short wavelength, high frequency light would knock electrons out of the metal, but long wavelength, low frequency light wouldn't. So that had nothing to do with amplitude, the amount of light shined. It was the type of light. So Einstein proposed a particle nature for light. Which are photons. And the energy of a photon equals h times nu. Hey, what do you know? It's the same as Planck's quantization here. And then that equals hc over lambda. Because remember our inverse relationship between frequency and wavelength. Along similar lines, Einstein came up with E equals mc squared. Which is an energy and mass relationship, so that there is inherent energy in all matter. So what is the apparent mass of a photon? Well, you could actually calculate this if you wanted to, and I'm not going to go ahead and do that, but you'd find that it's really, 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 really tiny. Now, another experiment, or another eventually experiment, that looked at different types of particle and wave behavior involved the opposite. If light, which was thought of as a wave, can be a particle, what about things like electrons, which are thought of as particles? Can they be waves? And the answer is yes. And we have de Broglie's equation, which is wavelength equals h over mass times velocity. So v is our velocity of the particle. So you could see that h is a very small number. Sorry about that. H is a very small number. And if the mass is big, and even if the velocity is big, but we're going to end up with a very, very, very small number for something that has a large mass. And so we'd have a very small wavelength, and we'd essentially have something localized in space. You can try this if you want with, say, a baseball. So you know Planck's constant. You can look up the mass of a baseball. Forget it's 5 ounces, something like that. And convert that, of course, to grams, or kilograms, I think. And then the velocity, you could convert, let's say, a fastball thrown at 90 miles an hour, convert that to meters per second, and see what the wavelength of light actually is. That's kind of a fun little thing to do, that you'll see what the wavelength is. So, by de Broglie's equation, the wavelength of an electron is 7.27 times 10 to the 11th meters, which is on the same order as the spacing between atoms in crystal structures or in compounds, whether they're covalent or ionic. So we can have something called diffraction, which is light that's scattered by a regular array of points or lines. So you can get then what are called diffraction patterns arising from interference of light waves. The interference can either be constructive or destructive. And only waves can really explain diffraction patterns. And so the question is, if an electron has a wavelength of 7.27 times 10 to the minus 11th meters, which is about the size of the spacing between atoms, it should diffract. Does it? Yes. Electrons diffract. So thus electrons have a wave-like nature. So we have light, which was thought of as a wave that has particle-like nature at times, and electrons, which are thought of as particles, have wave-like nature at times. So in reality, they're both particle and wave, depending on the type of experiment that you're doing. All right, well, I think that's it for now. In the next lecture video, we'll look at the atomic spectrum of hydrogen and the Bohr model of the atom. Until then, stay safe out there. Bye now.